All right, so we'll get started. Just two reminders items now, 11 or 12. Homework number 12 is due on Monday, okay? And we will have our exam on Wednesday. Um, so, so the past couple of days, the positive cases for COVID has been going up very quickly. So there's discussion of if we will be going online, but it's not decided yet. So it looks like up to this point, it's not decided. So let's still plan on having exam on Wednesday in seat over here. Okay. So um, if it did, the university decide to go online, then we'll do the exam online in an online fashion. Okay. So let me just put this out for right now. So if that happens, so then we'll have a Zoom proctoring exam. So that means I'll so you'll probably need to find a table where you can put your laptop actually in this direction, like on the sideway. So then you can adjust it so I can see your table when you are working on this. Okay. I'll probably put the exam on the screen there. So I'll try to make them all the problems on one screen so you don't have to flip it over. Okay. So we will see about that. I think that should be working. Okay, but hopefully we will have in-person class, in-person exam, so don't have to deal with that. Okay, just in case. All right, and this will be the last time we meet for lecture. So the next time will be on next week, Friday, Wednesday. Okay, so because we'll be done with the lecture after today. Okay, so we don't meet for the next three scheduled lecture, but we'll meet on Wednesday next week. Okay. All right. So today we'll be looking at a few just problems here and then doing some problem solving here. Okay. So the first problem we'll be looking at this guy. This one, you have a 2 kilogram block lies at rest on a frictionless table. A spring with a spring constant given as 100 newtons per meter is attached to the wall and to the block. A second block of 0.50 kilogram is placed on top of the first one. The 2.0 kilogram block is gently pulled to a position x equal to plus a and released from rest. There's a coefficient of friction of 4.45 between the two blocks. What's the period of the oscillation? Okay, so let me sketch the problem here for you guys. All right, I will stop sharing for a moment here. So this is the problem over here. There's a wall. There's a spring attached to a larger block. Okay, and then there's a small block on top of it. Okay, so this is being pulled at, let me say, probably equilibrium point. Let's assume it's somewhere here. This is the amplitude. Okay, so this is where x equal to 0. The surface here is smooth, but between these two blocks, okay, there's a coefficient of mu s, I think. All right, it didn't specify if it's a static or connected, but we'll assume this is a static. I think it says the two is not moving with respect to each other, so 0.45 here. Okay, m1 it's on top here, or you can call it small m, or and then this one is bigger m. Okay, so small m is 0.50 kilogram The larger is 2.00 kilogram. All right, it tells you the spring constant is 100 newtons per meter, and it's asking you what's the period of the oscillation. Okay, so if the two they are not moving relative to each other, then you just treat them as one system. Okay, one larger mass of capital M plus small m. Okay, so you can use the equation of the period equals 2 pi square root of k over m. I believe that's the equation. Let me make sure. Just double check. It's actually m over k. So in this case, then you would add the two up, right? The capital M and the small m up. So probably for part A, that's what you are going to do. You are going to just plug in the numbers. Hobby is asking what's the largest amplitude of motion that will allow the blocks to oscillate without the smaller ones sliding off. Okay, so it's looking for amplitude, maximum amplitude. So that means so the largest amplitude of motion, that means you have a motion of amplitude that is large enough. So then you are having this one is about to slide off. So then the static friction on this one will be maximum, right? On the smaller one. Okay, I think it's easier to focus on the smaller one here. Then the only force on the smaller one here in the horizontal direction will be just the static friction, right? If you want to look on this one, then you have to consider the static friction there and then also the spring force. So that might be more complicated because you have extra force there. Okay, so I think I can give you guys a few minutes, then we can take a look on this one together. All right, so I think we can take a look here together now. I believe you should be able to do this, right? Just plugging numbers. So 2 pi square root of 0.5 plus 2, they are both in kilograms, divided by 100 newtons per meter. Okay, everything is in SI unit, so your answer should be also in SI unit. Okay, so roughly 0.9935. If you want to keep 2 digits as the variables are, then 0.99. Okay, so part A, that's straightforward. On part B, so let's take a look here. You have this small one and then this larger one. Okay, so as I say, it might be easier to focus on the smaller block. So then on the small block here, the only force in the, so in the vertical direction, you should still expect like mg and the n, those two will cancel out, right? Now, if you pull this guy to the left, okay, so then it's going to, for the whole thing, it's going to go this in this direction, right? It will start to move in that direction. Then this guy will probably have the let me see, it's probably going to have something at this point. Yeah, it's going to be also having that. So if that guy goes there, actually it's going to be the other way around. Okay, so going there, that will be the static friction. Okay, at that moment. But anyway, because it's static friction, so then the block will not be moving on the top there. So on this one, we can focus on this small block. Okay, so on small block, now the two, they are not having relative motion, so you can expect that this small block will have the same acceleration as the larger one, right? Because their motion will be the same, going back and forth, back and forth. Okay, so they will share the acceleration. So once you can figure out the acceleration on this one, then the acceleration for the larger one should be also fixed, can be solved. Okay, and then for the whole system. Okay, so for the small one, you can see that's the net force, right? The friction force is the net force. Okay, and then for static friction, we know it has a range from 0 to a maximum number, right? Mu s times m, where in this case, n will be equal to mg, right? So equals to mu s times mg, okay? And according to Newton's second law, net force should be equal to mass times acceleration, right? So we can put net force in terms of that guy or this, because they are the same, right? So then 0 is less or equal to m times a, less or equal to mu s times mg. Okay, so you can see this guy will cancel out this guy, and then it's 0 here, so it doesn't matter. Okay, so your oscillation should have a range from 0 to anything like mu s times g. Okay, mu s times g will be your maximum oscillation possible. Okay, so then that will be the same for the larger block. Okay, or the system. So the system will have, this will be the maximum oscillation, right? So A max. And then oscillation, because this is a simple harmonic motion, oscillation will be equal to A omega square. Okay, if you look at the equation for the equation of motion for simple harmonic motion, AT actually is equal to minus A omega square cosine of omega t plus phi, right? So then this is the maximum possible, right? Or this is A max, okay? So that tells you that when you are having maximum oscillation, so then this guy will be equal to that guy, okay? So then you can set it up that A times omega square equals to mu s times g, right? So then A will be equal to mu s times g divided by omega squared, okay? We have mu s, we have g, so omega, we should also be able to figure out omega, right? Because omega is equal to 2 pi over t, right? So then this guy you can actually calculate already. 2 pi divided by 0.9935 second, okay, will give you 6.324 per second or second inverse, okay. So this is your omega. Then take the numbers in here, you'll see 0.45 as your coefficient of static friction times 9.8 meters per second squared divided by 6.324 per second square. You can do radians per second, okay, if you want, because that's the dimensionless, okay, radians per second. So that will give you about 0.11. Yes, so 0.11 should be sufficient there. All right. So that's the maximum you can pull. If you pull your A, the amplitude larger than 0.11, okay, then the oscillation on the system or on a larger block will be larger than the maximum oscillation that smaller block have. Okay, so then smaller block will start to slide off of the top of that one. Okay, so this guy here. All right. Just let me know if you have questions before we move on to the next one here. All right. So the next one here, it says if a pendulum-driven clock gains 5.00 seconds a day, what fractional change in pendulum length must be made for it to keep perfect time? Okay, and for a pendulum-driven clock, usually the period is 2 seconds, so you can kind of imagine it goes like tick tock, right? So 2 seconds for the period. Okay, so give it a try. It should be a very, very, very small number. Okay, the adjustment should be a very small number. You can, I think, yeah, it's asking you to calculate this in fractional change. Okay, so because the change is very small, so you probably want to keep during your calculation, you want to keep a lot of digits. Okay, if you keep just like 2 or 3 digits, that might not be enough. Okay. I had to keep like 6 decimal points for this one. Okay. So I think the key here is to figure out what will be the period of this clock. Okay, and then compare to the ideal one, the perfect one. Perfect one is 2 seconds. Okay, Now it says it gains 5 seconds per day. So that means it actually should have a slightly less period, right? So then, for example, if you have a perfect period, exactly like the right clock, you'll expect, say, let me see, what's the cycle for the pendulum? It looks like quite like 40 something thousand cycle, right, in a day. So it go back and forth like 40 some cycle. And then for this clock, it has a couple more cycles than 40 something thousand, okay? So you can start from there to figure out, you should be figuring out first what's the current period for this clock, okay? And then using the period equals 2 pi. So that's, let me get you guys started maybe here. So the perfect one here, t is equal to 2 seconds. Okay, so this guy is equal to 2 seconds. So then you probably can figure out what's the length over there, or if you don't want to figure out that, that's fine, because you're just looking for fraction, right? So on this one, this is probably like 1.9999, whatever, maybe 8 or 7 after a few digits, something like that, okay? So you'll have a new period here, okay? And then you can solve for a new length over here. Then see how much is this in terms of this guy in fractional wise. So you'll be doing like L prime plus L, okay? And then for the adjustment, you just have to see about this. Okay, this one is probably going to be like 99.9 whatever percent, okay? So then the adjustment you need to do is 1 minus that, okay? All right, so let's take a look here. So we need to find out this one first, okay, T prime first, because it says games 5 seconds per day, but we actually do not know how much is this per cycle, okay? So let's see. So on this one over here, we need to divide by the total time, right? Total time, so T total in a day, right? In a day divided by the number of cycles, right? Number of cycles. That will give you this period, right? Because the total time in a day divided by number of cycles in a day will be giving you the period here, T prime. So let's see what's the total time in a day in terms of in seconds. So there are 24 hours. Each hour has 3,600 seconds, right? So that's how much time in seconds for a day. Number of cycles, all right? So number of cycles here should be 24 times 3,600 per second, right? Divided by 2 seconds, right? So this is the ideal clock, right? Number of cycles that it will have, okay? Now this new clock gains 5 seconds a day. So that means it has 5 seconds divided by 2, right? More cycles than the ideal clock, right? So it has about 2.5 more cycles than that one does, the ideal one does, okay? So that will give you what's the new period here, T prime. So that's how you figure that out, okay? So it's going to be 1.999884 seconds, okay? That's how much, how many digits I kept. All right. So once you have that, you can theoretically you can figure out this L prime, and then you can do the same thing over here. Okay. A lot of times I don't want to figure out the L or L prime because I can see that I can actually use a fraction here. So then I don't need to figure the L and L prime back. I can figure out the ratio already. Okay. So I'll call this equation 1, this equation 2. Okay. The same thing I'll be doing. I'll do, in this time I'll do equation 2 over equation 1. Okay. So then that gives me, on the left hand side, I have T prime over T. Okay. On the right hand side, I will have 2 pi square root of L prime over G divided by 2 pi square root of L over G. Okay. So then you can see the 2 pi can cancel out the G, and the G can cancel out. Okay. So then on the right hand side, this is equal to then L prime divided by L, right? Square root. Okay. So what I really need is the ratio of L prime over L. Okay. So then I can square both sides of equation here and here. So I will get my L prime over L equals to T prime over T squared. Okay. So then this would be 1.999884 seconds divided by 2 seconds. Okay. Squared. That will give me 0.999884. Okay. So you can see the length of this clock is little bit slightly less than the ideal one. Okay, so you want to make that adjustment. So that means you want to just make this little bit longer. Okay, so how much? Then it will be 1 minus this guy. That will be equal to percentage wise, it will be 0.0000116, or if you express that in percentage wise. Okay, so it's just roughly about, this is 1/100th of percent, right? Very small change there. Okay, so that should be your final answer there. Okay. All right. The last example here, we are going to check on this example. It says, consider the van der Waals potential. So this is the potential if you have two atoms or two molecules. Okay, so in the very small scale. Okay, so for example, like a gas, if you have the very dilute gas, they are very far apart compared to their sizes. Okay, so let's put it that way. Um, it says use the model to, this is used to model the potential energy function of the two molecules where the minimum potential is at R equals to R sub 0 or R naught. Find the force as a function of R. Consider a small displacement R equals to R0 plus R prime and use the binomial theorem to show that the force does approximate a Hooke's law. Okay, so that means the force is about or roughly equals to minus kx, okay, where k is a constant number. All right. So I can have you guys actually try to see if you can do this, but we can take a look on the solution together um, in a few minutes here. Okay. Now remember, so you probably want to do the expansion first to figure out potential as a function of x. Okay, so write x as, so in this case, x is equal to r prime over r naught. Okay, this should be a very small number, like very approximate to be 0, but just take it as some number. Okay, just use that as variable. And then for the force, if you remember, it should be minus d ur over d, or in this case, let's do x. Okay, in terms of x, over here. So I think this one might be a little bit challenging. So I will just show you guys the solution here. Okay. So um, it says R is equal to, just stop sharing for now. So in the problem, it stated that r is equal to r naught plus r prime, okay, which r prime is a small number. Okay. So then we can rewrite the potential energy equals to a constant number u naught times r naught over r naught plus r prime. Okay, the original one is r naught over r. Okay, so then we can rewrite it that way. To the 12th power minus 2 times r naught over r naught plus r prime to the 6th power. Okay. Now what you can do is here rewrite this guy. So this guy can be rewritten as you can divide both sides by, or the numerator by r naught and then denominator by r naught. So it becomes 1 over 1 plus r prime divided by capital R naught. Okay. So r prime is a small number, so that means this is a small number. Okay, so we can replace that as x equals to r prime over r naught. Okay, so just replace that one. So then this guy is equal to 1 over 1 plus x. Okay, this thing here is just 1 over 1 plus x. Okay, so then this then will be now becomes a function of x. Okay, equals to r naught or u naught 1 over 1 plus x to the 12 minus 2 times 1 over 1 plus x to the 6. Okay. Then this is equal to u naught of 1 plus x to the minus 12, right? Minus 2 times 1 plus x to the minus 6 order. Okay. Then we can apply binomial theorem here, which says this guy over here, 1 plus x to the n equals to whatever this long expansions, okay? Well, let me just copy it down over here, 1 plus x, so we can refer to it, okay? So equals to 1 plus n x plus n minus 1, 2 factorial x squared plus. All right. So then basically, you are going to apply the binomial theorem here to this term and then to this term, okay? So on the first term, your n will be equal to minus 12, okay? So then it's equal to, let's do it this way, okay? Let's do it this way. So 1 plus x to the minus 12, this is equal to, okay, apply this guy where n is equal to minus 12, right? So then equals 1 minus, right? 1 plus minus 12 becomes minus 12x plus, okay, n will be negative 12, and then negative 12 minus 1 over there, 2 factorial times x squared plus, okay? I think we don't need to keep the higher orders because higher orders are smaller numbers, okay? So in this case, if let's say, for example, if this x is very small, for example, 10 to the minus 6, right? Then this guy will be 10 to the minus 12, okay? Already very small number. And even though this is 12, we'll bring it down to 10 to the minus 4. So this is minus 6, then this will be minus 10, okay? Then the higher orders you can actually ignore because it will be much smaller, okay? So we can just put it in that way. This would be equal to 1 minus 12x, then let me see, plus this will be 12, this will be 13, right? 12 times 13 will be 156, okay, divided by 2 factorial, that means 2 multiplied by 1, so it'll be 2, okay? X squared, and then plus the higher orders, okay? This guy here, 1 plus x minus 6, then equals to, similarly, it will be 1 minus 6, x plus 2 factorial minus 6 minus 1, right? X squared plus higher order terms. So it will be 1 minus 6x plus minus 6 times minus 7. So it'll be 42, okay? And then divided by 2. So 42 divided by 2, x squared plus. All right. So, and this term, there's a factor of 2 in front. So you can put 2 here, which means 2 multiplied by this, right? Equals 2 multiplied by all this, okay? So then becomes 2 minus 12x plus, okay? This would be 42 x squared plus da da da. This guy would be 78, okay? 156 over 2 will be 78, all right? Now we will take, so this is equal to that. This is equal to that guy, okay? We'll put this one in here, and then this one in here, okay? So potential as a function of x then equal to mu naught. So the first one will be 1 minus 12x plus 78x squared plus da da da. Okay, so the first one here minus the second one. I'm just going to move it down here so we can line up the terms. Okay, plus 42x squared plus da 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 there. Okay, so then 1 minus 2 gives you minus 1. Okay, so then equals to mu naught minus 1. This one and this one will cancel out. Okay, and 78 minus 42 will give you 36. Plus the higher order terms, okay? We don't actually have to worry about the higher order terms because they will be small, negligible, okay? So then this is your UX, all right? But we are actually looking for the force between the molecules, right? That means we need to look for the Fx, that will be equal to minus derivative of Ux over dx, okay? So if you do derivative to the potential energy, then it gives you the interaction force between the two molecules, okay? So you're pretty much doing derivative to that guy, okay? So then the first term here is constant, it's not a function of x, right? So that goes to 0. The second term will become 2 comes down and then becomes x, okay? So it will be minus of u naught times 2 times 36, right? Times x, okay? So then fx is equal to minus of 72 times u naught times x, right? All right. Now this is f as a function of x, okay? We need to return to the original one here. F in terms of, so x is equal to r prime divided by r0, r naught, okay, capital R naught. So f in terms of f prime, or r prime, okay, is equal to, then you just replace it over here, minus 72 mu u naught over r naught times r prime, okay? So this is the variable. Now this is a constant, right? So this is the constant k, you can say that's constant k. So then your f as a function of r prime should be minus k r prime. So this is pretty much the Hooke's law, right? So that's what it wants, okay? So mu naught is the constant, R naught is constant, 72 is constant, okay? So it's just that. All right, so I think that would do it for it, okay? Just don't worry about this one will not be in the exam, okay? Just relax. But I wanted to show you like for the moleculars, they can actually, so if you take chemistry, you probably learn that the moleculars will be vibrating, right? Around a certain position. So this is where it's from, okay? So because basically the interaction between the moleculars can be modeled as a Hooke's law. So that means it will vibrate, okay? Back and forth, okay? All right. So then I'll see you guys on next Wednesday for the final exam, either in class or online, okay?